We'll now work through an example that illustrates some important features of the electric flux. Consider a sphere of radius r centered on a single point charge q as shown. The flux simply counts the number of lines passing through the surface. Since every line from the charge passes through the sphere, the flux must just be equal to q over epsilon naught. This flux can also be calculated mathematically. In particular, the flux is always equal to the integral of E dot dA. Since the electric field is everywhere perpendicular to the surface of the sphere, E dot dA here becomes simply E times dA. Further, since the electric field has the same value at all points on the surface of the sphere, we can move E outside the integral, and the integral is then just equal to A, the surface area of the sphere. Therefore, we see that for this case, the flux is just equal to the magnitude of the electric field at the surface of the sphere multiplied by the surface area of that sphere. Now let's take one hemisphere and expand it to a radius of 2r and connect the two hemispheres with a circular plane at the equator as shown. Note that all of the lines still pass through our new object, now composed of 3 surfaces. Therefore, the total flux through this new object must be the same as it was through the initial sphere of radius r. In fact, you can see that exactly half of the lines pass through the small hemisphere, half of the lines pass through the large hemisphere, and no lines pass through the plane. When we calculate the flux, we verify this observation. Namely, the surface area of the hemisphere of radius 2r is equal to 4 times the surface area of the hemisphere of radius r. But the electric field at the surface of the large hemisphere is 1/4 of the electric field at the surface of the small hemisphere. Consequently, the flux through each hemisphere, E times A, is the same and just equal to half of the charge Q divided by epsilon naught. What about the plane connecting the hemispheres? We saw that there were no lines passing through the surface. Therefore, we expect the flux to be 0. In fact, the flux is 0, because the direction of the electric field, i.e. the direction of the field lines, is parallel to the surface. Therefore, E dot dA is 0 everywhere on this surface. We'll now move on to establish the relationship between the flux through any closed surface and the charge that's inside.